Hello everyone. In last two lectures, we have seen how to find out integrating factor using different types. Today, we are going to see the third type for finding integrating factor. In this type, if function is connected with y into dx plus another function is connected with x into dy equals to 0. If given example is matching with this pattern, then we find out the combination of m into x minus n to y. Provided that this is non-zero, then the integrating factor is 1 upon this factor mx minus n into y. Let's have examples on this. Here we can easily see the y is separated with some function of x and y into dx plus x into separated into some function of x and y into dy equals to 0. So this example is perfectly matching with the standard form. Therefore, before applying the rule, we will go to verify whether function is exact or not. So matching given example with mdx plus ndy form, we get m as, we'll open the bracket, xy square minus 2x square y cube, and whereas n is x square y minus x cube y square. Now we will differentiate m partially with respect to y. So we are getting 2xy plus with respect to y, 2x square is constant and differentiation of y cube is a 3y square. So altogether we can write 3x square y square. Whereas dou n by dou x is 2xy minus 3x square y square. You can see 2xy and 2xy. This is similar, but this is 6x square y square, but this is minus 3x square y square. That's why we get non-equality. So dou m upon dou y is not equals to dou n by dou x. And so we get the non-exactness of given differential equation. Now question is how to make it exact. So we know if we multiply given differential equation by some factor, then it will be exact. So we are in the third type, how to get that factor. So before that, we have to check x into m minus y into n. This should not be 0. Let's check. So x into m becomes x square y square plus 2x cube y cube. This is x into m minus y into n. So let's multiply n with y. So we are getting x square y square minus x cube y cube. So in subtraction we are getting x square minus y square cancellation, and 2x cube y cube plus x cube y cube is 3x cube y cube. We wanted this non-zero, so we got it. Therefore, by this third rule, we have integrating factor as 1 upon this factor 3x cube y cube. Now we call given differential equation as 1, and which was non-exact originally. Now if you multiply given differential equation 1 by this factor 1 upon 3x cube y cube, it becomes exact. So let's multiply. We claim that this is exact differential equation, and we match this with mdx plus ndy, so we get new m and new n for the calculation. So before going for integration, let's simplify this equation as, if we separate numerator with this plus sign and this minus sign and then cancelling x and y accordingly, we get this is our new m and this is our new n. So we know how to solve exact differential equation. We integrate m with respect to x as, we get 1 upon 3x square y, 2 upon 3x with respect to x. So 1 upon 3y constant and 1 upon x square is derivative of minus 1 by x. So its integral is minus 1 by x plus 2 by 3, and integral of 1 by x is log x plus c1 as some integral constant. We call it equation 2. Now we solve n by taking only those terms which are free from x. So we write it here, x free n with respect to y. So in this n, only this term is free from x, so we'll collect it only minus 1 upon 3y dy. So its integral with respect to y is minus 1 by 3 constant, and 1 by y is integrated as log y plus c2 as equation 3. So we know solution is addition of equation 2 and 3. So solution is given by minus 1 upon 3xy plus 2 by 3 log x minus 1 by 3 log y equals to some constant c. So either leave this like, or we can multiply by minus sign to make the term positive. So this way we can find out the solution of given differential equation, which was originally not exact. Let's have another example. In this example, so some function is multiplied by y into dx, and again some function is multiplied by x into dy equal to 0. So this is of third type only. So let's check first whether it is exact or not. So we have m, along with that y inside, we get x into y square sine of xy plus y into cos of xy. Let's differentiate this m with respect to y partially. So x constant, and we have y into sine xy, a product of two y functions. So uv rule will be used. So first, as it is, derivative of sine xy is a cos of xy into derivative of xy, that is x, plus second as it is means sine of xy as it is, and derivative of y square is 2y. Whereas second term is also product of two functions of y. So uv rule again, y into cos of xy is differentiated as minus sine of xy into x plus cos of xy as it is, and derivative of y is 1, this way. So if we open the brackets, we get x square into y square cos of xy plus 2xy sine of xy plus, actually it is minus x into y sine of xy plus cos of xy. So finally you can see, so these two can be clubbed middle terms. So we left with x square y square cos of xy, 2xy sine xy minus xy sine y is 1xy sine xy plus cos of xy. This is what the dou m by dou y. Now let's have n, which is x into some function. So we are given with x square y sine of xy minus x cos of xy. We have to see what is dou n by dou x. So for that purpose, y is constant. So x and sine of xy are the product of two functions. That's why u into v for x. Therefore, first as it is, sin xy is differentiated as cos xy into derivative of xy is y with respect to x, plus now derivative of x square is 2x. So first term is done, minus second term is also a product of two functions with respect to x. So uv rule, x as it is cos xy becomes minus of sin xy into y, plus second as it is, so cos of xy as it is, and derivative of x is 1. If you open the bracket, we get x square y square cos of xy plus 2xy sin xy minus plus xy sin xy sin xy minus cos of xy. If you see, x square y square cos xy x square y square cos xy is same. Xy sin xy, and this is 3xy sin xy, so it is not matching, whereas this is also cos xy and this is negative of cos xy. So with this we can say dou m upon dou y is not equals to dou n by dou x, which gives you the differential equation is non-exact. Now we go to find out integrating factor which makes given differential equation exact. We check s into m minus y into n. So if we multiply m with x, we get x square y square sine of xy plus xy cos of xy. This is x into m minus y into n becomes x square y square sine of xy minus xy cos of xy. If you open the bracket, we get cancellation of x square y square with negative x square y square sin xy, and we left with 2 times xy cos of xy, and which is non-zero. That's why integrating factor is 1 upon this. So 1 upon 2xy cos of xy. Now what we'll do, we got the integrating factor, we multiply given differential equation which we call it equation 1, we divide it throughout by 2xy cos xy, and we claim it is exact. Now let's multiply given differential equation by 1 upon 2xy cos xy. Now how to solve this? Let's separate them. You can see x and y getting cancelled. So after simplification we get y by 2, x and y is getting cancelled. Sin upon cos is tan of xy plus, here cos and cos is getting cancelled along with y, only 1 by 2x is remain dx plus, in the next bracket xy is getting cancelled, we are getting x upon 2, and sin upon cos gives you tan of xy minus cos xy is getting cancelled along with x, and we left with only 1 by 2y dy. So we get here mdx plus ndy form in simplified way. So this is exact. We claim that this is exact. So how to solve this? It is integral of mdx is integral of y by 2 tan of xy plus 1 upon 2x dx. So y by 2 is constant and integral of tan xy. So integral of tan xy can be taken as integral of sin xy upon cos xy. So if we take it like this, if we take integral of tan xy as a sin xy upon cos of xy, then we can check derivative of cos xy, which is a denominator, is negative of sin xy at numerator, so we can make minus sign available, into derivative of xy, which is y. So if we multiply by y and divide by, so we can do adjustment like this, minus 1 upon y and integral y sin xy upon cos of xy with negative sign, and dx, we can easily see it is minus 1 by y log of denominator. So you can see derivative of cos xy is a minus of sin xy into y, so which is a perfect numerator. So in this case we get integral as log of denominator, so log of xy. Or you can write, if you don't want to write to minus sign, you can write this as 1 by y log of sec of xy. So this is putting this integral value into example. We get minus 1 by y log of cos of xy, that's it, plus 1 by 2 and integral of 1 by x is log x. This is what the integral of mdx plus some integral constant, say c1. This is what the equation 2. Now we take the x-free terms in n for the next integral. So x-free n with respect to y. So this is our n, mdx ndy. This is our n in which this contains x, so we will not take it. So only minus 1 by 2y we can take for integral. So 1 by 2y dy. So minus half is outside and 1 by y is integrated as log of y plus say c2, equation 3. So solution is equation 2 plus 3. So we can cancel this y and we have minus half log of cos of xy plus half of log of x minus half of log of y equal to some constant. For a moment take it that constant also half of log of c. C is any arbitrary constant, that's why we can take it. So we can remove half throughout. This can be written as log of, using this minus sign, it can be written as log of sec of xy. This can be written as log of sec of xy. This is plus log of x minus this is log of y. This is log of c. So using the log property, we can have log of a plus log of b is log of a into b. So x into sec of xy we can write, and minus log y can be written as log of denominator y equals to log of c. That's why finally we can write x into sec of xy whole upon y equals to c. So this is what the answer we could write. So this way, if given differential equation is non-exact but it is of the type y into some function f1 dx plus x into some function f2 dy equals to 0, then we can find out integrating factor this way.